The chemical shift of a signal is determined by its local electronic environment for a given set of chemically equivalent protons. Protons in the vicinity of an electron withdrawing group or a pi bond have signals whose chemical shifts is toward the left end of the spectrum, or downfield, or sometimes we call that deshielded. The right side of the spectrum is referred to as the upfield part of the spectrum. Proton signals that are upfield are further away from electron withdrawing and pi bonding functional groups. If we look at this spectrum of ethanol as an example, you'll see that the HBs over here are more on the left side of the spectrum, whereas HAs, which are further away from the OH group, are on the right side of the spectrum. All right, so the protons that are upfield are shielded, meaning that nearby electrons reduce the field experienced by the protons. So in the applied magnetic field of the NMR, which is shown right here by B0, the electrons that surround the nucleus, right here, circulate perpendicular to the applied magnetic field, and they actually induce their own magnetic field in the direction opposite of the magnetic field. So this reduces the size of the applied field that a nucleus is exposed to and reduces the energy needed for resonance, and it gives more of an upfield chemical shift. So these electrons are really shielding the nucleus from B0. So the nucleus doesn't feel as much of it. So when there are electron withdrawing groups and functional groups nearby a nucleus, they draw electron density away from the nucleus, leaving it more exposed to the applied magnetic field. Because of the greater exposure to the magnetic field, the energy required for resonance is increased, and the nucleus is said to be deshielded. So deshielded nuclei have downfield signals in the NMR spectrum. And you can see that in this table here, where the more electronegative groups have sucked some of this electron density away from the nucleus. They've deshielded it, and so the nucleus feels more of the applied magnetic field, and it takes more energy to spin flip the nuclei. So the electron withdrawing groups, as can be seen over here, have the greatest impact on the protons bonded to the alpha carbon, the one right next door, and then the effect kind of decreases as we go further away. Okay, so let's kind of look at an overview of where we see different functional groups on the NMR, and you can see, in this range we were just looking at those halogens, and then if you have oxygen or nitrogen, or the halogens over here, and then interestingly, and we'll come back to this in a second, we get alkenes and aromatics. Carbonyls are really deshielded, and the most deshielded protons that we see are on the carboxylic acids. And those are really removing electron density from this proton, and it's almost like this proton, remember this proton's pretty acidic, so it's had a lot of its electron density removed from it, so it's very deshielded. Now, for alcohols, amines, and actually any other group that's hydrogen bonding, a wide range of functional groups is observed, so you can see this range down here at the bottom. These protons can be expected to be found anywhere from like 1.5 parts per million to 5.5, and their chemical shift is dependent upon concentration because that's going to determine how much hydrogen bonding there is. And the more extensive the hydrogen bonding there you have in a solution, the more deshielded the protons are. So it will really change depending on temperature and other environmental circumstances. So let's look at the effects of pi bonding on the chemical shift. Protons bonded to a carbon-carbon pi bond, like the alkyne or the alkene or an aromatic, are found in the 4.5 to 8 parts per million. Actually, alkynes, you can see, are lower than that, which is kind of downfield considering that there are no electronegative elements to deshield the proton. So instead of deshielding from electron withdrawing groups, carbon-carbon pi bonds actually induce a magnetic field that adds to the applied field, resulting in a larger field felt by the nucleus, and more energy is required for resonance. So the induced magnetic field in benzene is referred to as a ring current over here. And in the applied magnetic field of the NMR, the pi electrons in a benzene ring move around the ring. It's kind of like a spinning charge, and they induce their own magnetic fields perpendicular to the ring, and that adds to the applied magnetic field experienced at the nucleus. So resonance for protons on the benzene ring require a higher energy radiation, radio frequency radiation than protons bonded to sp3 hybridized carbons. And the downfield chemical shift of an alkene occurs for similar reasons. You can see the alkyne is actually a little bit different in the way that it's oriented in the magnetic field, and that's why the alkyne absorbs more upfield. So you can use this information to figure out sort of which chemical shifts belong to which protons in a molecule. For instance, if HA, HB, and HC, just take a moment and see if you can identify which ones you would expect to be most deshielded and which ones you would expect to be most upfielded or shielded. All right, so I think that this one should be HA and then HC, and then the effects are additive. So this one is HB. It's having electron withdrawing from both the carbonyl and the oxygen on the other side of it.